Hi there, welcome back to Weather Analysis with Mr. CB. We're going to be talking about the steps for temperature forecasting. So we already talked about in the last video some of the important things to think about with temperature forecasting, but we're now going to really talk about um, the steps. So the first thing that you want to do, look at the surface charts. So you can easily find these online and they're going to show you what are the current conditions. What type of air mass do you have? You want to think about that. Is there thermal advection? Do we have cloud cover going on? Where are the highs and lows? Are there any fronts? Is there moisture? These are all things that will affect the current conditions and affect the temperature forecast. So you want to think about how cloud cover is going to affect things. So if you have cloud cover, it is going to limit our diurnal processes, which are the fact that we get obviously warmer during the day due to the sun's radiation and the earth radiating that. Um, and then of course we're going to cool at night. But if we have cloud cover, we are limited in how much we can heat up and how much we can cool down at day and night. You want to note the height, type, and thickness of these clouds. Next, you want to verify model data. What you put in is what you put out. So basically, you're going to look at the models and see how they're handling the current conditions. If right now it's wrong, like let's say it says that it's 62, but it's really 54, well, that's a problem. So that might not be a model you want to use because what you put in is what you get out. So inaccurate observations, inaccurate data compounds over time and is going to be more inaccurate. So you need to make sure that the model that you're going to use, you should observe multiple, but the one that you end up wanting to use, make sure that it's handling these current conditions correct. Compare the model with current surface observations or SKUTs or ASOS data. All of those are quite accurate. So maybe the model is showing that it's too cold, too warm, too dry, could be any of those. Then you want to compare the models with each other. So let's say for a particular time, you're trying to find the high and low, and we can see, um, you know, which models performed the best and worst. So the NBM, GFS, and Euro, you can see what their low and high was, and then what it actually ended up being. Compare that at the end and see which one did the best. Observe trends in the models. So see how the model is changing over time. On pivotal weather, um, which we can show this more in a future video, but on pivotal weather, um, you can go to different runs, model runs. So what that means, a different model run is going to show the same time period, but it was issued at a different time. So over time, see how those model runs for the same time change. Maybe the temperature is increasing. So with each new run that they release, the high temperature for Tuesday is increasing. Then you might say, well, if that trend is occurring, then maybe it will end up actually being higher than the most recent run. You also want to think about the max temperature. Identify if there's thermal advection, see where winds are coming from, what air will they bring. Look at the top of the PBL, and we are able to use the temperature at the top of the PBL, which is at approximately 850 millibars for flat areas, 700 millibars for mountainous areas. But you want to use that, um, and it can help us determine the high. So what we can do is say, what is the temperature at 850? Then you will add 5.5 times 5. Now, why? Well, this is for Fahrenheit, by the way, but if you remember, um, an air parcel that sinks, we use the dry adiabatic lapse rate, which is 10 degrees Celsius per kilometer, but also that is 5.5 degrees Fahrenheit per kilometer. Um, and or per 1,000 feet. I'm sorry, per 1,000 feet. 5.5 degrees per 1,000 feet. So since it's approximately 5,000 feet above, you do 5.5 times 5. And why do you add that? Because temperatures are going to be warmer closer to the surface generally. And that can help you know the max temperature. Using a sounding, you can also look at a sounding to help you know the max temperature. Look at the temperature at about 850 millibars, follow the dry adiabat down to the surface, and determine the temperature there and add 2 degrees Celsius for a superadiabatic contact layer correction. This is only useful for clear sky days, sorry, with diabatic heating. Next, you want to look at moss. Moss is being faded out a little bit. Remember, we talked about that in a few videos ago, but it still has some relevant uses. How does the moss compare to the raw data? Learn the trends in moss for a region. Then you want to make a forecast. We're really just talking about temperature in this video, but you want to say your low and high temperature, and then check your forecast after, see how it performed. Um, and that's basically the process. Now, what are some obstacles that we can have with temperature forecasting? Well, frontal systems are going to be an obstacle because the highs and lows for our days might be at atypical times. Usually, our highest temperature in the day is close to before sunset, because that's what the maximum amount of heating has been able to occur, and the low is right before sunrise typically. But sometimes if frontal systems exist, that can change things. The timing of the front is key. Then for terrain, mountain ranges are heavily impacted by winds. Winds are going to change your high and low temperature. And it also depends on if you're on the windward or leeward side. There's also variance with the planetary boundary layer. And precipitation can change your temperatures. For example, if you have a lot of precipitation, that can result in evaporative cooling. And if you remember, FDC are our cooling processes. Okay, sorry, completely messed up. Those are our warming processes. MES, E for evaporation, are our cooling processes. Um, and that is going to lower our maximum since it's a cooling process. Obstacles, further obstacles. Standing water from rain. If you have standing water, well, that's going to evaporate, which, as we mentioned, is a cooling process, so it's going to lower the max. Unexpected snow on the ground can melt, and if it melts, that's cooling process, and if it refreezes, freezing is a warming process, so then that might increase our high. So you have to think about these things when you're making your forecast. So bottom line, you're just going to basically look at many models and decide which ones are performing the best and use the conditions that you know there to be right now and um, your surface data, and combining that, you should be able to create your temperature forecast. So now that we've talked about that, let's actually look on pivotalweather.com and see um, some of what we can do. So we want to go to models, and what you can do, you want to make sure that you are in the version where it says return to previous experience. If you do not say that, click on this option because you want to make sure you have this slider. So you can see the different models right here. You can choose from them. Common ones that you might want to use, GFS right there. You might want to use the NAM. Might want to take a look at the HER. You might want to take a look at, oh, sorry. You might want to take a look at the Euro. So we're on the GFS, but let's actually go to temperature since that's what we were talking about. So I'm going to say 2 meter temperature. And okay, that's what I wanted. So you can see, let's just look for a random location. So you can even go zoom in more. Regional. Let's go here, southeast. How about that? So you can see this area in South Carolina, it is showing 60. And you can see the, the max that it's showing. We see 80 as a high. Well, you can click on a different run to see what it shows. Still 80 for the run before that. S- Still 80. We can go quite further back. Now is at 76. Sorry, kind of hard to see with the sunglasses on. Um, so you can just compare that and then go on to other models and you can see the trends over time. So you can see it went from 76 to 80, so it increased, but relatively stable around 80. But also it would be important to compare this with current conditions, see how this is handling the current conditions at hour zero. So that's what you would want to see.